Yeah, this talk is sensory mechanisms underlying cybersickness, and I think this is kind of an interesting opportunity to crosstalk between simulation and training community and this community. So this work comes out of specifically flight simulation, so we're dynamically controlling flying vehicles, and every dimension that I talk about here is relevant. We've talked about a bunch of things this week where maybe pieces that are relevant and pieces that aren't, like for example if you're doing static stereo views, not all of this applies. So I'm talking about the full case. So in flight simulation, we're concerned with perceiving and regulating motion, and we're talking about using virtual and extended reality devices to do that work, and what are the implications. So we need to start out by identifying the senses that are involved in perceiving and regulating motion, and we can identify 5 sense systems. So there's, of course, vision, there's equilibrioception, which has to do with our sense of balance and spatial orientation and is centered on our vestibular organs. Of course, hearing's involved. We have our proprioception, which is our sense of our body control, what we're controlling, the forces that we're exerting, the things that are happening to us. And we have our somatosensory system, which is kind of our environmental awareness. And all of these things work together in terms of perception and regulation. So I think there's some interesting perspective from flight simulation. So we have these full flight simulators on the left, which are the kind of the pinnacle devices. Those motion legs provide very realistic and well-timed motion cues. These devices are built around a particular kind of immersive visual system. So it's a cross-cockpit collimator. It typically goes out to at least 200 degrees. We have cases horizontal, and we have cases that go as far as 300. It is a particular arrangement that bounces light off a mirror and provides parallel light to the eyes, which is unlike off of any screen you'll ever look at, and so it provides a great sense of depth. And so inside the simulator, we have an environment that provides a very naturalistic experience of looking far, having to focus near on the physical cockpit, interact with the normal physical things, and so normal focus, refocus, scan, and gaze patterns are intrinsic to this, as well as a perfectly high fidelity physical and social environment for controlling the aircraft. So if we want to take this device and take an array, and we have other kind of wraparound immersive displays that we use, like this one on the left, so cylinders and domes and things. If we want to take an arrangement where we have a separate immersive display around a near physical cockpit and then collapse the presentation of all visual elements through a single set of near eye optics, we're doing something fairly profound, and the purpose of this talk is to think through what that is. And at the top, I would point out a salient feature, which is the fact that we provide a left eye and a right eye image to each eye on a panel that is at a fixed optical distance in front of each eye, and that's a major fact in the whole situation. So I'm going to analyze this in a series of 5 topics that are of generally increasing intricacy. And the bulk of this talk is really concerned with how the images are delivered, not what is delivered, but I want to take a moment at the top to talk a little bit about image content and optical flow. So this is a field that's been studied a lot, and there's a really excellent study from 2022 by O and Son that systematizes the whole field and provides actually a wonderful baseline for the field. And so they had the requisite literature survey, but what they really contributed was they systematically constructed a set of 52 dynamic scenes and ran a large study population through those scenes. They measured the response of the subjects, both subjectively with questionnaires and objectively with physiological measures in an HTC Vive. So they systematically went through all kinds of content variations, so roles, translations, complex moves, different fields of view, reference frames, so is there something fixed, controlled and uncontrolled situations, and duration. And I'm not going to say much about duration in this talk, but duration is a major word in this whole field. longer exposures are more problematic. The findings were the most provocative factors were scene content that had significant roll, pitch, and long duration. And high provocation included high-speed content with acceleration, translations in sort of unusual directions, so up, down, and backward, lack of a reference frame, lack of control, and larger fields of view were more provocative than small fields of view. And I'm going to come back to field of view repeatedly, and at the end, that's a major consideration. We're in flight simulation, we're accustomed to total field of view, and there are a lot of, I think we have maybe the most expansive view of what that is. And in terms of the study, I would comment that of the original study population, about 7% dropped out. That means that they experienced severe cyber sickness and said, I can't go on, and they quit. The results were based on the 75% of the population that got through the entire study and did not include that 7%. Okay, so on to the main part. So in visual systems, we always start with field of view, and on top, I want to distinguish field of view, which is what you see instantaneously in your visual field, versus field of regard, which is what is accessible over time by moving your head. And a feature of virtual and mixed reality systems is that you do have 360-degree field of regard, but that's, there is something fundamentally different about that than field of view. So on the left, we have a depiction of the human horizontal field of view, which is extremely sharp right down the middle. It falls off various ways as you deviate from that central optical axis. You get to about plus minus 60, and you're at the extent of your binocular vision. So that's the part of your visual field where you have everything you're looking at, you have information coming in through both the left and right eye. Then beyond that, there's another 50 degrees or so of monocular peripheral where only one eye picks up what's out there. Then on the right, we have a similar arrangement vertically. It's slightly down biased because we're more concerned with the ground than we are with the sky, but that's kind of how it lays out. So if you take that, and on the left side of this slide here, you superimpose that on a fovea-centered set of visual eccentricity rings, you get this picture on the left. So the dark shaded region in the middle is the binocular region, and you have sort of the nasal obstruction depicted in the bottom part of that, and then you have the monocular region shaded more lightly surrounding that. If you go over to the right side of this and you take that, and now you superimpose the fields of view of a variety of head-worn displays on there, you see, okay, in the best cases, and maybe this picture is about 5 years old, maybe in today's best cases it might be a little bit more. The best case you're doing is covering most of the binocular field. You're completely missing the monocular peripheral. Okay, so truncating the peripheral is a feature of these devices, and it's a big deal. So briefly thinking about peripheral vision, so I think we all understand that we have this very sharp peak of cones at the center of our vision that provides, all the wonderful central vision features we have, surrounded by a much larger region of rods that provide a monitoring function. Importantly, they pick up information that helps inform and guide our saccades, which point those cones at important things in the feature and integrate, the rich visual scenes we experience over time. So pilots rely on their peripheral in a number of ways to do their job, I walked into this just assuming that peripheral meant this monocular region out here. In the research, I found out that it's actually not that precisely defined in vision science, and I'm going to so quantifying where the peripheral is actually needs to be done, and I'm going to come back to that at the end. So that's topic number one. Topic number two is encapsulated in the title of this paper quoted here: cybersickness in head-mounted displays is caused by differences in the user's virtual and physical head pose. So that's a narrow claim, and this particular study was looking at pitch, and it demonstrated convincingly that latency in updating the image content to track pitch was nauseogenic. And this particular finding has been replicated with other motions besides pitch, so it's pretty robust. So what comes out of this is that it is necessary to have very accurate and very low latency head position measurement that then is immediately with very, very low latency fed into the imaging chain so that the image is rendered from the proper perspective. Latency is certainly not getting latency right is one of the shortest paths to making people sick. Where I come from, that's amateur. I don't want to dwell on it, but I mean, you just got to get it right. And I would also note that because of the limitations of field of view, head-worn displays do provoke extra head movements, and depending on what you're talking about, that can be negative. So in some aspects of aviation training, that can actually be negative training and even dangerous. So the third topic is visual vestibular conflicts, and so this gets into the whole field of sensing motion, visually induced sensation of motion, and non-visually induced sense of motion. So of the 5 senses identified, the 2 primary senses for detecting motion are vision and equilibrioception. So visual is the strongest for linear motion, so translation through space. Vestibular is strongest for rotational motion, and visually sensed motion is actually a very strong cue, and anybody who works in flight simulation knows this. We've experienced it, throughout our careers. And as we've already noted, it's truncated in extended reality. So so we work around these immersive display systems. We've experienced just a little thing in the peripheral moving us. I showed you a simulator at the top where we can have motion cues that line up with physical motion cues that synchronize with visual motion cues. But there are classes of flight, like fighter airplanes, where it is not feasible to provide accurate motion cues. So those are no motion simulators, and yet there's a very powerful sense of motion in those simulators by way of the visually induced motion field. And we're going to come back to that again towards the end, exactly where that is. When we think about the vestibular organs, we need to separate the control side and the perception side. So the control side, there are reflexes that bypass the brain, where the vestibular organs have direct control over the body. There are 3 of them that are listed here. The most salient for our purposes is the vestibular ocular reflex, which stabilizes your gaze in the presence of head movement, body movement, so that we have a stable visual field. That's an extremely fast reflex. It's in the 5 to 10 millisecond range, so it's one of the fastest things in the body. I submit that is actually the spec for latency in your image generation pipeline. Perception is slower. It's in the brain. It's an integration of all the senses I identified at the top. What the brain does is amazing. Nobody really understands it, but it's really it's just amazing. Okay, so fourth topic, a little bit more elaborate. So this is going to be depth perception and divergence accommodation conflict. So. And so we're confining ourselves to kind of the aspects of depth perception that are influenced by the kind of device we're talking about. So if I want to look at a thing and I'm not quite on it and I need to rotate my eyes to point at it, there's a disparity that I'm resolving with a divergence movement. If I'm looking at a thing and I'm not quite focused on it, and I focus my lens in my eye, that's an accommodation movement. So Disparity and blur are the cues, divergence and accommodation are the responses, and the geometry of these two things is the same. They're cross-coupled in a natural setting. It works phenomenally well, and it's depicted in this little picture on the right, where this figure is focused on this apple and pear in the near field, and has that kind of bottle in the far field, the left and right views, left and right eye simulations, and sort of a simulation of what the retinal blur looks like in a natural situation. So if we go into a situation where we're putting the image on a screen, we are colliding with this. So we've introduced a screen, and now we focus on the screen. So the accommodation locks on where the screen is, and we all know that 2D images can convey tremendous sense of depth. There are many cues that are capturable in 2D. So we've fixed accommodation, but divergence is going to vary with scene content. And so if we go to the picture on the lower right, the left panel, so the A and C is sort of a natural situation where the eyes are looking into the corner of that hinge. They're focused there, and you see sort of in C the simulation of natural blur. Move over to the B and D column, and now the accommodation is on the screen. But the disparity fixation is behind the screen in the corner of that hinge. So that's an uncrossed disparity. So if you think of looking at a thing and then looking behind it kind of up and out, that's uncrossed. And you see kind of the simulation of the image below, it's sharp. So our images are photorealistic. So that's a bit of a conflict there. So over on the left, we have the opposite situation where there's an image that is in front of the screen. So that is a cross disparity. So if you think about looking at a thing and then kind of coming down and in, that's crossed. So that's the divergence accommodation conflict. That's what's going on there. And it's a big deal. It's been studied a lot. A lot of people put a lot of money into trying to find solutions to it. I don't really see anything out there at this point. So the best study of its effects was and is the one from Shibata in 2011. And this picture on the right kind of summarizes the findings pretty succinctly. So we have divergence on the x-axis plotted versus focal distance on the y-axis. Both are in diopters, so that's inverse meters. The way you read it is the origin is far, the upper right is near, the 45-degree angle is where the screen is. It's also a natural viewing situation, and it's comfortable. So if you're starting to look at content that moves away from that screen, then you're moving off that 45-degree in either the cross or uncrossed direction, and it becomes increasingly difficult and uncomfortable to put the images together. And at a point you can't, and you get double vision. So there are a couple of sort of top findings that fall out of this. So there's an implication that there is a limited comfortable tolerance range for divergence accommodation conflict that humans have, and it's estimated at about 1/4 to 1/2 diopter. Another thing that comes out of this study is that the most uncomfortable conflict is the near conflict, so the image in front of the panel. And in the case of aviation training, that is the case of looking at your cockpit instruments and not out the window. And we'll amplify this a little bit more in the next section, which is binocular stereoscopic displays. So this is the most complicated piece of the whole thing. So several components. So there's the device itself, the alignment of the device itself and the device to the human. This picture of this guy in this helmet, that is an F-35 pilot. That is an F-35 helmet. They wear that helmet 100% of the time when they're flying that plane. this, and it's kind of a augmented and mixed reality device. I mean, you can see clear out the window, but they have a variety of enhancements that get projected onto this helmet. So this thing has a 2-day alignment process to itself and to the particular user. And I think that's maybe a bit of an index as to how hard the alignment and problem is and how precise it needs to be. And of course, we're not going to invest anything like that in a virtual or a mixed reality device. But you know, this thing is more complicated, but it doesn't get different physics. And there's this nice illustration here on the right from a paper that Meta published a little over a year ago about some of the mismatches. So there's head tracking and eye tracking on the left. The middle, if you have cameras that are picking up the near physical environment, they are not in the same place that the eyes are, so that has to be, the pass-through has to be reprojected. And then finally, there's the fitment of the headset to the wearer, and then the maintenance of the fitment of the headset to the wearer. Both of those are issues. So all that's one collection of issues. Then there is stereoscopic pipeline distortions. So there's a whole series of papers that I think fundamentally lay out how prone the stereoscopic pipeline is to introducing distortions. So the original in the series is from Andrew, and Ellie's paper yesterday went through 3 of these. So you know, but what I'm actually more interested in is kind of the effects on a dynamic image stream. So what are the dynamic if you're doing a dynamic stereoscopic scene, what are the distortions going through that pipeline dynamically, and what is the effect of those distortions? And I would point to this paper, Instability of the Perceived World, from Huang and Pelley in 2014 as probably the most compelling collection of hypotheses. I think they're largely true, but there has not been all that much downstream study to validate those hypotheses. In terms of image content and distortions, there's a fairly recent study that's in this chart at the lower right from Z et al. In 2023 that used optical distortion. So it had a high degree of optical distortion, a middle degree of optical distortion, and a negligible degree of optical distortion. And it showed that, you know, with time, and the duration on the x-axis here is, getting into 30, 40 minutes on the right, the highly distorted, differentially increased discomfort. And then finally, there's, I think, the cautionary related experience. We had some discussion about this here yesterday, but the 3D cinema and television, I submit, it's really hard to get around the fact that they crashed pretty hard and fast in around 2012. They were going to be the next big thing. They did crash pretty hard and fast, and whatever the seeds of revival are, that happened. And I think it's cautionary, and I think I have maybe a fundamental explanation as to why here below. So if we're going to be talking about binocular vision and stereoscopic vision systems, I think we need to understand binocular geometry. So this picture here is sort of a classic understanding from the mid to late 1800s. So down at the bottom, we have sort of the human with 2 eyes looking out, and we have this concept of the horopter, which is the locus of points that project on the same pair of points on the retina. And from a purely geometric argument, that is circle, so the set of circles you see here. But by that time, people had the geometric argument actually went back to the Middle Ages, but by that time, people understood that the human physiology didn't follow that pure geometry, that it was more like this set of curves that is concave nearby and flexes out to convex far away, and has a region of tolerance around the ideal line. So that thing is called the empirical horopter. So people more recently have been studying very precisely how this thing is shaped. And so these blue lines here are the latest estimate of the shape of the horopter, and we have both the horizontal and the vertical depicted here. And the pink shaded regions are sort of the area of fusion the fusible area around it, and it's notably much, much larger at a more eccentric position than right down the middle. The bump in the horopter is consistent with the idea that we want something, we want to fixate on something in our central vision, and then have a surround that we're less concerned with. And of course we have the shape, and we also have this backward tilt in the vertical horopter. And so this is not a thing we learn. This is innate. This is inbuilt to our system. So it's an innate and infinite family of matchable binocular regions that are dependent on fixation. So what happens when we introduce screens into this? So that's how natural binocular vision works. So we introduce a screen. So we got these pink lines, and so the screen is going to fix accommodation, and it clashes with the natural correspondence geometry. So it doesn't have the concave to convex. It doesn't have the backward tilt. It essentially is, amplifies the divergence accommodation conflict. So stereoscopic content practices basically recommend putting your content at a distance like where the screen is. And we heard all about that yesterday. We heard in great depth from Disney and others about how they do that. And to me, in the 3D theater last night, it was very, very obvious that everybody who was going after a mass market or had a big budget was doing that. I mean, they were putting their content near where that screen is. And that's the whole game. They understand that. So, but in flight simulation, we have kind of a challenge, because we have a mostly bimodal task distribution. So we have to look near at the instruments, and then we have to look far. And I mean, there are some cases, and actually some critical cases, that are in between, especially in helicoptering or taxiing an airplane. But most of the tasks are either out there or right here, and that doesn't seem to fit very well with this. So the next thing to ask has to do with depth cues. And so this picture over here on the right is from NASA, and it lists a whole bunch of depth cues, and some of them are pictorial and lighting and so forth. On the x-axis, we have distance to the thing we're looking at, log distance, and on the y-axis, we have increasing ability to resolve fine detail. Just going to pull out two cues here. So on the lower left there, we have accommodation and convergence, and those are weak cues, and they operate close by. Then a little farther out, we have binocular disparity, and that is a more precise cue, but it has a finite range. And so when I was puzzling out how all this worked, I went outside one day and I was trying to discover where the just noticeable difference was between my left eye and right eye perspective, and I concluded that it was about a quarter mile. So a few hundred meters, that's actually what this chart says. So one thing that follows from that is there is no binocular disparity information available beyond a few hundred meters. There's none. So the whole binocular stereoscopic thing cannot add information beyond that distance. All right, a bit of a shift here. So, but all within this topic. So eye movements. So there's a really fascinating paper from about 2 years ago out of UC Berkeley called The Statistics of Eye Movements and Binocular Disparities on VR Gaming. I can only pluck the conclusion given time constraints. Basically, they find that VR has subtle but significant distortion of eye movement patterns. So in the lower visual field where you're looking near, it shifts away from crossed towards uncrossed. It does not match the vertical tilt of the horopter, and it does not match the curvature of the horizontal horopter. So I'm just going to quote the author's conclusion. I mean, these guys are top authorities in the field. We hypothesize that solving the binocular correspondence problem, obtaining fusion, obtaining precise stereo vision, and making accurate verges during saccadic eye movements are compromised in the VR gaming environment. Doesn't mean it's impossible, but I mean that's a thing that is happening. So we talked about stereo pipeline distortions, just a little depiction of expansions, compressions, shears, shifts. Okay, observer position. I think this is actually a pretty interesting point. So observer movement relative to the screen can distort the presentation of the image. And so you've got 6 degrees of freedom that you can move in, and 5 of the 6 degrees of freedom distort the image. The only one that doesn't is pitch, because it preserves the frontal nature of the image is preserved. Roll is particularly stressful because of the vertical vergence eye movements required to compensate for it are notably stressful. So this is a major point in favor of head-worn displays, because by affixing the display to the head, you eliminate all of these mismatches. And if you have accurate and latent and low latency head tracking, you also eliminate motion parallax distortion. So this is a fundamental reason to believe that head-worn displays are a superior way to present and experience 3D stereoscopic content versus fixed displays that the user can move freely in relation to. Okay, last point. So I've been talking about field of view from top to bottom. At the very end of my research, I found what I thought was a really interesting clue in an old paper from 2009 from Paponier et al. And this was done in a cave. Shout out to Mr. Sandine. What these guys surveyed the vision science literature and were kind of assessing central and peripheral vision. So the vision science literature kind of came down in neuroanatomical and functional camps. It had a range of definitions. The field had not coalesced or converged around any of them. The one on the right here, 60 degrees, that actually is the same definition that I use in flight simulation. So it's out there, it's in the literature, but there didn't seem to be any consensus around that. But what these guys did is they created a set of patterns that stimulated the central visual field, the peripheral visual field, and the full visual field. And they exposed their users to them statically and dynamically. And when they did it dynamically, they varied the frequency of exposure. And what they found is that the visual sense of motion was stimulated by dynamic peripheral optical flow. Not central, not static. And they ended up defining the central vision range is extending to somewhere between 7 and 15 degrees. So that's eccentricity from the optical axis. And they couldn't say it any more precisely because of experimental limitation. But okay, this is some experimental evidence that says that there are peripheral effects much closer in than flight simulation thinks. But there seems to be very little in the vision science literature that really works with that. So there's this very widespread observation, I hope I planted it correctly at the top, that reducing field of view reduces cybersickness. So why is that? I mean, I've wondered why that would be. And so I want to throw out a hypothesis. And the hypothesis is that reducing field of view reduces the region of exposure to image distortions that mostly provide false visually induced motion cues. And so it's prevention of false visually induced motion, which is nauseogenic. I think that's a studyable question. So, all right, so how am I doing on time? Okay, so I'm going to wrap up here. So 5 clusters of sensory mismatch and limitation, limited field of view, differences in virtual and physical head pose, visual and vestibular conflicts, vergence accommodation conflict, and the whole stereoscopic complex. So the significance of this work is it's a unique analysis, distillation, and synthesis of a large body of manufacturer research. There's a lot going on in this field. Cybersickness turns out to be a powerful lens. It's a clue that something's wrong. Analysis of causes leads to mechanisms. Mechanisms leads to studyable questions. I'm in the poster session. I'm deferring my thoughts about the research agenda to the poster session, so if you're interested, please come talk to me. That's it. So, questions?